Assalamualaikum warahmatullahi wabarakatuh, and warm greetings to all the panels, lecturers, and all the viewers. My name is Muhammad Izaimi, and today I will be presenting my final year project entitled Optimization of Impressed Anode Design on Impressed Current Cathodic Protection System for Oil Platform Structure. Okay, moving on to the slide. Corrosion is a natural phenomenon as metal tend to revert back to their natural state when reacting with the environment. The harsh environment of seawater, which houses many platforms, are causing considerable amount of corrosion-related issues. As the corrosion weakens the strength of material, the consequences may lead to serious problems and cause failure on the offshore infrastructure, which is usually costly to repair. Studies and decisions regarding the future integrity of offshore structure and its component is very significant as it depends on accurate assessment of conditions affecting the corrosion process and the rate of deterioration. Nowadays, ICCP is one of the most popular methods of corrosion prevention at offshore structure. The approach takes advantage of natural electrochemical reaction of material, where it shifts the potential of the structure in order to maintain them as a cathode, which will not corrode in the presence of an anode. To do that, impressed anode need to supply sufficient current to raise the potential of the structure to a level where negligible corrosion occurs. Besides of its ability that able to provide unlimited current output capacity, it is very effective and economical for large structures such as the offshore structure, as it is cheaper in a long-term application. The objective of this study are, first, to develop and simulate a three-dimensional ICCP model for an oil platform submerged in seawater. Second, to analyze the effect of impressed anode location and current output to the protection profile of the platform. Third, to execute optimization of impressed anode location and current output in the ICCP model. The scopes are: develop the oil platform structure that is submerged in a defined seawater, perform the grid independent test to obtain suitable match, simulate the ICCP model for the oil platform using conventional multiphysics software based on the data and parameter collected in literature review. Next, study the effect of anode design parameter, which is the distance and the output current. And lastly, find the range of the anode distance and current that maintain the ICCP protection at the platform. Moving on to the literature review. So, the ideal anode of ICCP system must be capable of passing the required current into the seawater environment. As most offshore structure has a long lifetime, the anode used are the inert type one, such as the metal oxide or platinized anodes. According to the table shown, besides having a very low consumption rate, this anode have a high current density range, which gives them the ability to drive high current. This allows the anode to be placed remotely from the structure by protecting the large areas of the offshore structure at a certain distance. In ICCP, the impressed anode receives current supply from a transformer rectifier unit, which is located at the cellar deck level at the platform structure. So the current is supplied through a submerged cable lying on the seabed. So in order to monitor the cathodic protection, the silver chloride seawater electrode are used to measure the potential of the platform. Basically, the ICCP should ensure that the structure is within the range of protective potential, which is in between the negative 0.8 volt and negative 1.05 volt, as stated in the table. So, corrosion activity will occur if the potential is higher than negative 0.8, as well as ICCP should not overprotect the structure above the negative 1.05 limit. This will cause hydrogen evolution to initiate and cause additional problem to the steel structure. Moving on to the simulation part, the numerical modeling of the ICCP system are done using the commercial COMSOL multiphysics software, where the boundary element method is utilized to simulate the system. From the slide, we can see the governing equation of the BEM. Besides that, the Button-Volmer equation is used to describe the electrode reaction, which is at the steel surface structure. Basically, this is the flow of work of this system study. First, develop the model geometry. Then, include the physics for the ICCP system. Then, the grid independence test is done to obtain the most suitable match. After that, the simulation is run from the collected data of the past research. Upon successful doing that, we will study the effect of anode current allocation to the potential distribution and the local current density of the platform structure. Lastly, optimization is done to find the range of current and distance that is protected from corrosion. In simulation, the first thing to do is develop the model geometry. The model geometry developed is the 92-meter high steel oil platform, the seawater domain, and the cylindrical anode. Note that the anode distance computed in this simulation model is measured from the nearest surface of platform to the anode. Basically, this is our whole model geometry developed. This huge cylinder is the seawater domain, and this is our oil platform. And then there is the anode located with respect to the oil platform. In this initial simulation, we set as 30-meter distance from the anode to the oil platform. After that, we set up the ICCP physics into the simulation model. We use the secondary distribution interface in the COMSOL software, and this is the definition that are applied into the simulations. These data are collected from the published papers and journals. The grid independent tests are conducted to find the most suitable mesh element size setting. In this study, the max potential is measured in the test, and its output value is plotted against increasing number of mesh elements. After a few iterations, constant data output was generated showing that the mesh is at optimum size and it don't have to be refined further. Shown here is the mesh element size setting used and the mesh model that is produced, which will be used for the each simulation process throughout the study. The simulation of ICCP model on oil platform structure is finally run by using the parameter in the table, and this is the output produced by the software. We can see here on how the platform is protected from the current supplied from the anode. For information, the parameter used for this first simulation is taken from a past research by Wang. As example, the anode distance is 30 meter and the anode output current is 230 ampere. I am to remind you that most of this parameter is kept constant in the next study unless changes is stated. The distribution of platform potential of this initial simulation. As referred to the legend, the platform is well protected by the ICCP system as the potential is in between the cathodic protection range. Moving on, the first anode parameter studied is the effect of anode current output to the protection of platform. Here we only manipulate the amount of current injected by the anode. From the graph here, we can see that the local current density at platform is decreasing as we increase current applied at anode. We can deduce that more corrosion activities at platform surface is suppressed as the current is increased. Next, we also analyze the potential distribution at the platform surface as we vary the current at anode. In platform A, the applied current is 1 ampere and the structure is clearly underprotected as the potential is way higher than the maximum limit of the protective potential. However, the 150 ampere applied platform B is fully protected as the potential is within the cathodic protection limit. In platform C, the current output at the anode is 500 ampere. From the potential distribution, the platform is overprotected as its minimum potential crossed the negative 1.05 volt limit. In conclusion, we found that low current output by the anode is simply not enough to stop corrosion activities. Meanwhile, excess current will result to overprotection at the protected structure. In ICCP, to reduce cost, a lower current output is more desirable as the system have to protect the platform throughout its lifetime. Optimization is done to find the range of current that is enough to ensure protection at the platform at certain distance. In this graph, the maximum and minimum platform protection is computed for a wide range of current input and plotted down. We can see that the distance 30, the platform is protected in between current range of 54 ampere until 325 ampere. The anode distance effect is studied in here, so only the distance parameter is manipulated. We find that a very close anode will cause overpotential at platform. Example, at platform A, the anode distance is 4 meter. The non-colored region shows the part that is overprotected. Also, a further anode distance will give a more uniform potential distribution at the platform. Example is at platform B, anode distance is 190 meter and we can see that the distribution of the platform is homogeneous. Both conclusions is supported by the plot graph of local current density above, where at a higher distance the maximum and minimum values become closer to each other. We optimize anode location to find the range of distance that is enough to protect the platform at a certain current applied. Usually, shorter distance is preferable to cut costs from having a longer anode cables. However, sometimes longer distance is applied due to more uniform potential is received by the platform. In the graph, the protective range of anode distance starts at 18 meter for the anode current of 230 ampere. Next, the optimization of the combination of current and distance parameters is computed from the range of input shown here. This is the plots of maximum platform potential versus anode current and distance combination. Meanwhile, this is the plot of minimum platform potential versus the combination of anode current and distance. Both plots shown previously is overlapped to find the protected region of the platform at any distance or current combination. From the surface plot here, we can see that any current below than 50 ampere is not protecting at all. Plus, designer can find the best anode location combination with their desired current output, or lowest current applied at distance they required. From this data also, we can compute the range of distance which is suitable for different type of anode, as different type of impulse anode have different current density capacity. As a conclusion, the research is successfully done to simulate the ICCP model of platform structure. The effect of anode current and distance is analyzed and verified by the past study by Wang. And lastly, the optimization has been done in the experiment. Thank you for your attention. Feel free to click the like button below and subscribe to this channel.